to the end of chapter 16. Hopefully this will be a short video here, just talking about 16.6 expected value, teaching you how to win some money, or at least how to be aware that everyone is taking your money. So let's jump right into it. All right, did not expect that buzzer to play again. Anyway, the expected value is, there's a lot of notation here, so let's kind of run through it. So the expected value, that's just the symbol for expected value over here, E of x. This symbol here, that is sigma, the Greek letter, and what it means in math is it means the sum. Okay, so what this formula means is the sum of every x times every p of x. All right, x is just every outcome. Okay, and so in our case, in most of these examples, those are going to be payoffs. So you're winning $2, you're losing $100, who knows? And then p of x is just going to be the probability of each outcome. So what it's really going to look like is going to look something like this. To calculate these expected values, it's like this first outcome, x1, times its corresponding probability, plus our second outcome times the corresponding probability, plus our third outcome times the corresponding probability. I think you get the idea. However many there are. Okay? And so this expected value of a game is 0, then we call that a fair game. Okay? Both you and you're not expected to win or lose any money in the game. So now we kind of know expected value. Let's jump into some examples. All right, example 1. So we have a spinner. We're going to assume it's free to play. And if your spinner lands in one of these 3 regions, you'll either win $3, win $5, or lose $6. So what I'm going to do is just kind of make a little table displaying my outcomes and the probabilities of each of those outcomes. And so our possible outcomes are you win $3, you win $5, or you lose $6. Not the most beautiful table in the world. So probability of losing $6, it's going to be the easiest to figure out here. It's just going to be 1/4, so 0.25. Those other regions, those are equivalent. So each half of 270 degrees, so 135 each. So 135 over 360 is 0.375. Beautiful. So once we have this, we are ready to go. So to figure out the expected value here, it is going to be just each outcome times the corresponding probability. And we're just summing that up. All right, a little bit of calculating here. And I get okay. So what this means, if we got this 1.5, $1.50, okay, it means that for every, we're expected to win, all right, for a single spin of this spinner, $1.50. All right, so naturally we are never going to win exactly $1.50, okay. I hope that's pretty obvious based on the spinner. You can only win 3 to 5 or lose 6. But over the long run, all right, on average, okay, this is going to be about the expected value of every spin right here. Since it is not 0, it is not a fair game, although in this case, it is working out in our favor, okay? Because over the long run, we're expected to win money on this game. So if no one's charging you to play this game, I would spin this spinner all day, because I mean, over the long run, you're averaging a winning of $1.50 each time you spin. All right, example 2. So you're rolling 2 dice, if the sum of the two rolled dice is 8 or more, you win $2. If not, you lose $1. All right. So I'm going to make my probability model again right here. The payoffs, we know if the sum is over 8, you win $2. Sum is under 8, you lose $1. All right, so probabilities. We've gone over kind of sums of dice rolls before. So 8 and above, there's going to be 36 possibilities. For 8 and above, it'll cover 15 of them. For below 8, it's just 1 minus that, so 21. So once you have the probability model, figuring out the expected value is quite easy. And that's to solve for part A. If you're trying to show that it's not a fair game, all you got to do is just show that the expected value is not 0. So figuring out that expected value, it's going to be $2. All right, cool. So I'm going to get, so what is this? We have 30 over 36 minus 21 over 36, which equals 9 over 36, which is just 1/4, or 25 cents. Okay, so it's not a fair game because the expected value is not 0. It's 25 cents. All right, so for part B, to have a fair game, the $2 winning should instead be what amount? Okay, so this is basically just got to set up a little equation here and solve. In order to have a fair game, we need our expected value to be 0. So I'm going to set that equal to 0. Change the 2 here to x. All right, I'm just trying to solve for what winning would make this expected value 0. Everything else will stay the same. The probabilities have not changed. And I'm not changing the losing outcome of minus $1. All right, so let's multiply by 36, get rid of some fractions here. So 15x equals 21. X equals 21 over 15. So x equals $1.40. Okay, so you would want to change that $2 winning to $1.40 to make it if you wanted to make it a fair game. Okay, meaning fair game, once again, expected value of 0. All right, last example. All the numbers are going to get a little bigger, so it may take us some time. State lottery, 6 numbers are randomly chosen without repetition from the numbers 1 through 40. If you correctly pick all 6 numbers, only 5 of 6, only 4 of 6, you win $1 million, $1,000, or $100 respectively. What is the value of a $1 lottery ticket? All right, so I'm going to ignore the whole $1 thing for now. Okay, I really need to kind of get my probabilities. So, kind of thinking the table, we need to, if you pick all 6 correct, you pick only 5, or you pick only 4. Okay. And obviously there's a lot of other scenarios here. You can pick 3, you could pick 2, you could pick 1, you could pick 0. But in all instances, the payoff in those cases is 0. So we really don't need to account for this. Okay, we really only need to account for these scenarios. So if you pick 6, you win $1 million. You pick 5, you win 1,000. Pick 4, you win 100. Now we got to figure out the corresponding probabilities. So the probability of picking 6 here, I'm just going to use those combinations. All right, the total number of ways to pick 6 from 40 is 40, choose 6. Okay, and The numerator there is just going to be 626, which will give us a very small number. Make sure you include the right amount of zeros here. All right, so unlikely that you are winning the million. That's all right. I'll take 1,000. Let's see how likely that one is. So in this case, once again, same numerator, 42.6. All right, so now we need to choose 5 of the 6. And for our last number, it can be any of the remaining 34. So it'll be 0.000053. And for the last one, well, once again, probably not going to happen. Okay, I'll take $100. So following the same pattern here for the probability, denominator still 42.6. Now of the 6 numbers, we want to choose 4. And then we can choose any of the remaining 34. And I get 0.0022. All right, so let's start getting this expected value going. So once again, it's probability of each outcome times that payoff. So it's going to be 1 million times 0.0000026 plus 1,000 times 0.000053 plus 100 times 0.0022, which equals I got 0.53. All right. Well, that's good news. That means a lottery ticket, you're gonna win money on average. Oh, wrong. We have not accounted for the value of the lottery ticket. We had to pay $1 for it. So we have to do the 53 cents minus the cost of the ticket, $1. And so in the long run, we're losing 47 cents on these lottery tickets. All right, that's it for this video. Short and sweet. Have a good one.